Good morning, children. Today we will discuss about graded index fiber structure. Graded index fiber structure. Let us go with the presentation. Okay. Today we will discuss about core index structure of graded index optical fiber. Already we have discussed the core index structure for the step index optical fiber. Now we will discuss core index structure for the graded index optical fiber. And here the important parameter while designing the graded index optical fiber, refractive index plays a vital role. So here if we consider the refractive index of the core, it decreases continuously with the increasing radial distance r from the center of the optical fiber. That means in the case of core, refractive index decreases continuously with the increasing radial distance r from the center of the optical fiber. But it is constant, the refractive index is constant in the cladding. So the most commonly used construction for the refractive index variation in the core is the power law relationship. Let us see. N of R is equals to N1 into 1 minus 2 delta R by a whole power alpha whole power 1 by 2 for R less than or equals to A, greater than or equals to 0. For R greater than or equals to A, which is N of R is equals to N1 into 1 minus 2 delta whole power 1 by 2, which is similar to N1 into 1 minus delta, which is equals to N2. So here delta is nothing but the refractive distance from the fiber axis. A is the radius of the core, N1 is the refractive index of the core, N2 is the refractive index of the cladding, and alpha is the dimensionless parameter which defines the shape of the index profile. Alpha plays a vital role here. Alpha defines the shape of the index profile. So index difference delta for the graded index fiber is given as delta is equals to n1 square, which is n1 is nothing but core refractive index. Here n2 is cladding refractive index. So delta, so index difference is equals to n1 square minus n2 square by 2 into n1 square, which is similar to the n1 minus n2 by n1. So approximation on the right hand side of this equation, this one n1 minus n2 by n1, which reduces right hand side of the equation reduces the expression for delta to that of the step index optical fiber. So that's why. So here delta is equals to n1 minus n2 by n1, which is same for the graded index optical fiber and also the step index optical fiber. So here for alpha equals to infinity, if you substitute here in this equation, alpha equals to infinity inside the core. So here it reduces to the step index profile n of r equals to n1. So here this is for graded index optical fiber. If you consider alpha equals to infinity, it gives the step index optical profile n of r equals to n1. Now let us see graded index numerical aperture. So what is numerical aperture? Numerical aperture is nothing but it is considered as the light gathering capacity of an optical fiber. Light gathering capacity of optical fiber is nothing but numerical aperture. Light gathering capacity of an optical fiber is nothing but numerical aperture. So here determine the numerical aperture for graded index fibers. It is more complex when we compare with the step index optical fiber because graded index optical fiber here it is a function of position across the core and face. And this is in contrast to the step index optical fiber. So here the numerical aperture is constant across the core. If we consider the step index optical fiber, numerical aperture is constant across the core. So geometrical optics consideration shows that light incident on the optical fiber at a particular position R will propagate as a guided mode only if it is within the local numerical aperture NA of R at that particular point. So local numerical aperture is defined as NA of R equals to n square of R minus n2 square whole power 1 by 2, which is similar to the NA of 0 root of 1 minus R by a whole power alpha for R less than or equals to A. For R greater than A, N of Na of R is equals to 0. That means the local numerical aperture for R greater than A is Na of R equals to 0. For R less than A, it is this one. So here the numerical aperture is defined as Na of 0 is equals to axial numerical aperture is defined as Na of 0 is equals to n square 0 minus n2 square whole power 1 by 2, which is equals to n1 square minus n2 square whole power 1 by 2, which is similar to n1 into root of 2 delta. So here we can answer. So here the comparison of the numerical apertures for fibers having various core index profiles. So here for alpha equals to 1, alpha equals to 2, alpha equals to 4. Already we have discussed alpha equals to infinity. It is first step index optical fiber. So here these are the some of the numerical apertures for the fibers having various core index profiles. So here we can observe here it is R by A and it is numerical aperture Na of R by Na of 0. So here the numerical aperture of a graded index optical fiber decreases from Na of 0 to 0, Na of 0 to 0 as R moves from the fiber axis to the core cladding boundary. That means whenever here the numerical aperture tends to 0, when R moves from the fiber axis to the core cladding boundary. So here a comparison of the numerical apertures for the fibers having various alpha profiles is shown in this particular figure. So number of bound modes in a graded index fiber is, so number of bound modes in a graded index fiber is given as mg equals to alpha by alpha plus 2 into a square k square n1 square delta, which is similar to alpha by alpha plus 2 into b square by 2. So here k is equals to 2 pi by lambda. So here in this one we will obtain by substituting all these values, we will obtain this one. And here if you consider fiber manufacturers, most of the fiber manufacturers typically choose a parabolic refractive index profile given by alpha equals to 2.0. Mostly they will use alpha equals to this one. This they will consider alpha equals to 2.0. So here in this case mg is equals to p square by 4, which is half of the number of modes supported by a step index optical fiber for which alpha equals to infinity. So that has the same v value as shown already we have discussed in the step index optical fiber. So when alpha equals to infinity, so that is for step index optical fiber, but mostly for the graded index optical fiber alpha value, most of the manufacturers they consider alpha equals to 2.0. In step index optical fiber m equals to v square by 2, but here mg is equals to v square by 4. So these are the bounded modes in the graded index optical fiber. Thank you.